Hello everyone. Today I'm going to be answering a question that you might have had before. And if you haven't, well, you probably read it on the slide, so you just asked it. I'm going to be answering to you, WTF is big data? Trying to censor myself, keep it PG, right? So to begin, that's me. I used to work as a data engineer at Braintree, so know a little bit about this stuff. So today, an overview of the journey I'm going to be taking you on. First, I'm going to tell you why you should even care about big data in the first place. Then, in order to understand big data, we have to understand what is not big data, so what we call traditional data. Then I'll be introducing what big data actually is, which is the main purpose of this talk. And then I'll be talking about the Hadoop ecosystem, which are some of the tools that we use to tackle the big data problem. So, to begin, my pal Eric, the Google CEO, know him personally, all that. So he actually said at a conference of some sort, there were 5 exabytes of information created between the dawn of civilization in 2003. Now, that information is created every 2 days. So whether or not this is true or not, you can probably conclude, okay, there's a lot of data being created, and that number is only going to get bigger. So old ways of dealing with data probably aren't going to work, hence why we have big data. So to begin, in the past 60 seconds, so probably since I've started talking, we've had 760,000 pictures sent on Snapchat, 4 million videos streamed on YouTube, 456,000 tweets posted onto Twitter, 46,740 photos posted onto Instagram. And there's more. 16 million text messages were sent. 156 million emails were sent as well. 45,700 Uber rides were made. 15,000 GIFs were sent on Facebook Messenger. 154,000 Skype calls were made. Yes, people apparently still use Skype. And of course, $51,892 worth of money were transferred via Venmo for my American friends. So what can we conclude from this? The volume, the speed, and the variety of data is only increasing. And it's not going to decrease anytime soon. But first, before we get to all that exciting stuff, we need to talk about traditional data, or otherwise known as the relational data model. If you could change. Okay, so when we think of traditional data, we think about our stereotypical relational databases, which you've probably worked with before. So this is your Microsoft SQL servers, your MariaDBs, your Redshifts, your Postgres, et cetera, et cetera. The main idea behind it is we have data. Data is stored in a database. Databases are composed of schemas. Schemas are basically information about the format of the data, such as this column is an integer, this column is a string. There's a primary key that's linked to this foreign key over here, all the relationships between data. Tables are stored in schemas, which is the format of the data. Tables contain records, and we can run queries against records stored in the database in order to get some sort of information about it. So we can basically, I like to put this into 3 layers. We have our compute layer, which is what we use to run queries to get information about the data. Schemas, which is our format, such as our metadata and relationships between data. And of course, storage, because what is a database without the actual data underneath it? So the problem with the relational database system is whenever we want to increase any one of these layers, we need to make the whole instance bigger. And a lot of time in the real world, this isn't really doable because, for example, if you have like Redshift running in AWS and you want to add a new node, you have to do something called redistribute the data. And so this can take weeks at a time, and then your whole system is down. You can't run any queries against it, and well, most operations don't allow that. So now we go into the main star of the show, which is big data itself, which you can probably assume is going to work a little differently from the relational data model. So there's a few common misconceptions. So when you hear big data, you're like, okay, we have lots of data. Clearly, we have a big data problem. This is mostly true, but it's not the only thing that causes you to have a big data problem. You can have lots of data, and a relational database method can be fine. So there's basically the 4 V's of big data, which is what we kind of use to determine whether or not we have a big data problem in the first place. So this includes volume, which should come as no surprise, which is the amount of data itself, the velocity, which is the speed the data needs to be processed, the speed it's being created, all that fun stuff. Variety, which basically means we have a bunch of different formats of data and the types the data comes in, and then veracity, which is the accuracy of the data itself. I'm not quite sure why this is included in it, because I would assume everyone would want accurate data, but it's there. So this is kind of what the big data model kind of looks like. So before everything, these 3 layers were coupled together, now they're separate. So our compute layer, our schemas, and storage are all like separated. So what's nice about this is if you want to increase your compute power, your storage, or your schemas, you only need to scale one of those layers individually. And a lot of the times this can be pretty elastic, so you can like spin up your compute power, bring it back down, and go back and forth to your heart desire, and you don't have to worry about affecting storage or schemas or any of that. So now we go into the Hadoop ecosystem, which is the tools that we basically use to tackle the big data problem. So if you ever Google big data or Hadoop ecosystem, you're going to get a scary looking thing like this, where there's like, oh geez, there's like 20 million bazillion things in here, and there's no way I'm going to be able to learn how to use all of these libraries and all of these things. So we're going to step it back a bit and just talk about my friend, the Hadoop Framework, which is this little yellow elephant here. So there's basically 4 components of the Hadoop framework. There's Hadoop Common, Hadoop Yarn, Hdfs, which stands for the Hadoop Distributed File System, and then Hadoop Mapreduce. The most important ones we'll focus on is the Hdfs and Hadoop Mapreduce, but I'll cover the other ones as well. So starting with Hadoop Common, it's exactly as it sounds, common utilities and libraries used across the other Hadoop modules, good software engineering principles, don't duplicate your code, all that fun stuff. So not really that exciting. Let's just move along. Hadoop Yarn, which stands for Yet Another Resource Negotiator, is kind of like the operating system of Hadoop. So basically, a resource and application manager, it manages and monitors your workflows. Nothing too exciting, but basically the operating system of the whole thing. And then we have Hdfs, which stands for Hadoop Distributed File System. So the Hadoop Distributed File System is basically a master-slave model, which is why the name node has a little crown on it. So basically, a file comes into the system. It gets split up into blocks, and these blocks get stored on different data nodes, which data nodes is exactly where data is stored, exactly as it sounds. But one of the nice things about the way the Hadoop Hdfs deals with it is it makes replicas of the blocks and puts them on multiple data nodes. So if you have a data node located on some server rack somewhere, that server rack goes down, you still have access to all your data because it's duplicated. The name node is basically kind of a mapping system, you can think of it. Because all this data is being split up everywhere, well, how are you going to find it? That's where our name node comes into play. It basically says, this is the name of our original file, and this is how it's been split up. We have block 1 over here, block 2 over here, block 3 over here, et cetera, et cetera. So when you run a query on it or so, it can be like, okay, the name node's like, I know how to get all this data and put it into a file so you can access it. This is just a more complicated, more detailed diagram of what I just showed. And then we get to Hadoop Mapreduce. So the formal definition for this is it's basically a framework or a process used to process large amounts of data across a Hadoop cluster. Okay, that's what it does, but how does it do it? Because it's going to do it differently than our friend Postgres. So Hadoop Mapreduce, this should come as no surprise. A Mapreduce job is divided into 2 parts, the mappers and the reducers. It's all in the name. So to give an example, let's say we want to write a Mapreduce job that is going to do something like take an input with a bunch of words and count how many occurrences there are of each word. How might we do this? Well, first of all, we start with our input. We need data to actually process. Then what happens is we split up this data into different sections, smaller pieces. Each of these pieces gets sent to a mapper. Each mapper, multiple, running in parallel, do the same job. So what in this case it's doing is clearly it's counting each occurrence of the word. Okay, so we're doing that, but we need to get the whole thing in total. So what happens is then it goes through a step called sorting or shuffling, which is just saying, okay, well, dogs, you're all going to go in this pile over here. Cats are going to go in this pile over here. Birds over here. Then this part, once it's been sorted, it gets sent to the reducers. The reducers run another job on the data, which basically in this case is the same thing as the mappers did, just counting up how many occurrences there are. Then at the end, we take all this data, we smush it together, and we got a result. The only thing, though, and this is something you'll run into if you ever try writing Mapreduce jobs from scratch, is they're very hard to write, especially the more complicated that they get. So in the Hadoop ecosystem, that big, beautiful photo I showed you earlier, there's actually 2 tools that are used a lot instead of actual pure Mapreduce. One of these is Hive. Hive is actually built on top of Mapreduce, and it takes a HiveQL query language, transforms it, and then turns it into Mapreduce jobs. So you basically write like a SQL instead of an actual Mapreduce job, and it takes care of everything under the covers for you. There's another similar thing, Pig, which takes a scripting language called Pig Latin and does the same thing, transforms it into Mapreduce jobs to just make it easier for the end user to make these jobs. So if you remember our 3 layers are compute, schemas, and storage. We can probably, okay, so the main things that we talked about are Hdfs and Mapreduce. So Mapreduce is used to process data, so we can probably make a safe assumption it's going to be related to the compute layer. Storage, the Hadoop distributed file system, is dealing with storing data and how do we access this data located on multiple machines. There's our storage. But then the problem arises, how are we dealing with our schemas? So in a traditional data setting, when we insert data into a database, the schema gets applied to the data right away. So that's why when you write an insert statement in SQL and you put like an integer instead of a string or whatever, it complains like, oh, invalid type or whatever, and that stuff is because the data lives in the database with the schema applied to it already. However, in a big data system, we use something called a schema on read. So when the data is sitting in whatever storage it's in, there is no schema applied to it. However, when we run a transaction against it and we grab the data from it, we can have the option of applying a schema to it. So the data exists unformatted, but we can have the opportunity to format it as we pull it out or read it out of the system. So this is when one of the properties of big data, which is variety, we can actually store all sorts of things in these systems. Like we can have videos, photos, and files and stuff, and like it doesn't have, since it's not stored with a schema attached to it, it's perfectly fine for us to do. And we can also apply multiple schemas to the same data. So that solves that mystery. So now basically we have our compute is our Hadoop Mapreduce, our schemas is schema on read, and then our storage is the Hdfs Hadoop distributed file system. So hopefully at the beginning of this talk you were like, what the F is big data? And hopefully now you're like, yeah, I know what it is, or at least kind of. So there's some more resources if you want to learn more. There's a great course on Udacity that talks about Intro to Hadoop and Mapreduce. And if you want these links or whatever, you can just email me. Or if you have any other questions or want to chat further, feel free to shoot me an email. And thank you.